kind of properties you have in between your source and your reflection point. So we need to really get the true angles from the reflectors. We want to do a proper inversion. And, oops. And this type of approaches also works in more complex geometry, not just in flat geometry. So this slide is from Sven, and he's happy to discuss this a bit more details with you later. The conventional AVO inversion, can we really distinguish the various types of gas sets in the present multiple transmission losses and mode conversions and whatnot? Are the currently available modeling software fast enough for routine full waveform inversion? Is the ray tracing package available from the Shavani group at the Czech Academy of Science suitable for routine full waveform inversion? These are based on Gaussian beam type inversion, not just a pure ray. So you can actually do a waveform inversion on that. Can we be implemented with global or local algorithms? And this is a debate on inversion always. Once again, the Bayesian approach about uncertainty estimates. What kind of parameter can we really realistically estimate from inverting surface data, or perhaps with the additional mole seismic data? Ultimate goal is really inverted for rock physics. To get there, we still with upscaling and downscaling issues. So the ultimate aim is still rock physics and the fluids, about the fluids in the rocks. So the other thing we want to talk about in work on in this consortium is estimated anisotropic parameters from well logs. What can we get? We know from acoustic log we can measure gamma. Can we constrain delta and epsilon using gamma? Can we use resistivity logs, including directional resistivity logs, to help us to do this kind of constraint? How can we integrate the use of offset and walk wave VSP data into our workflow for inversion, if you have that kind of data? In some places you do have that kind of data. And always core log integration was a question about dynamic versus static modulus for engineering purposes. So just want to show you a couple of quick examples of what I mean. This is a empirical lab measured data set on shells. It shows that there is, in general, a correlation between the P-wave anisotropy parameter epsilon and shear wave anisotropy parameter gamma. Okay. This part is, at least in principle, can be measured from acoustic logs, looking at the difference between the Stoney wave and the dipole data. Now, you can argue about size, scale, things like that, but at least in principle, you can measure gamma download. If you develop a relationship based on rock physics data, or even model, perhaps you can say something in general about epsilon, from which you can do your seismic anisotropy model. Global static and dynamic, this is really data that I pulled out from a long time ago, that I did with Dave Johnston back a long time ago. This is the static Buck modulus versus the dynamic Buck modulus, and the static is smaller usually. Static Buck modulus is really dealing with large strains and stresses. Dynamic is from wave propagation, and the static is the ones that you want to get to in engineering applications. Those kind of numbers, the static numbers are the ones that you want to use in your Frank modeling, etc. But how do you get there from a dynamic wave velocity type measurement downhole? Because we know that there is a difference between the static and dynamic. And there is some empirical data, certainly not enough, we hope to get more, that shows you that perhaps over the range of interest, they're fairly constant, and you can say, okay, I pull a 0.7 in this particular case as the first estimate, the difference between the static versus dynamic moduli. So ultimately, what do you get? New sponsors. Okay, obviously we can get some science report, papers, algorithms, the usual stuff. We have meetings. Now, one thing that I think we hope to get from each of you is a data set for analysis, a small data set with 2 wells and a small seismic. And over the last 2 consortium companies have done that, and I think those who have done that are very happy with the result. And it's a trial data set, see things whether work in that particular field. Now the caveat of that is, obviously we're not going to process a huge amount of data for consortium. It's just a few gathers and 1 or 2 wells. And also, if you contribute to a consortium, the data will remain. We will not show your result to anybody except at other consortium members at the meetings. Okay, so there are companies that have done that in the past, and I can honestly say that they've been quite happy about the result. Software, you get 1 license of IMOS and license and updates. Members only IMOS modules, and then the tools for anisotropic modeling inversion, and Sebastian will go a little bit more detail about the proposed tools that we're going to include in IMOS for this LRP3. Processing that are using workflows that are sponsors only, at least restricted, I think 1 year or during the duration of consortium. So, for example, the tablet processing, we haven't done it from other companies that are outside the consortium, although we've been approached. On-site training and consulting, you get 2 days on-site training on IMOS and whatever other consulting you would like us to do. I'm sure Gareth will be happy to negotiate with you. So, who are the ones who are doing it? Me, Scott, Franklin, Luis, Paula, Gary, Sven, Sebastius, one of Sebastius' associate at Wyoming, Steve Brown, who's at NDI at MIT now. We are a member of SEAM, some of you might know that, which is the SEG run seismic modeling consortium. And we're applying to participate in other consortium. So I think that's all I have. Yeah. So let's hold the questions. Unless you have immediate questions on this. And